Hello, my name is Yuval Filmus and I'm from the Technion. Today I'm going to talk to you about joint work with Noam Lifshitz from the Hebrew University in Jerusalem, Dor Mintzer from the Institute of Advanced Study in Princeton, and Elchanan Mossel from MIT. The subject is AND testing and robust judgment aggregation. So let's start. Consider the following scenario. We have a bunch of judges, in this case 3, and they have to decide whether an accused should be convicted or not. The accused should be convicted if they have both the means and the motive. So here we have 3 different judges, Judge Holmes, Judge Brandeis, and Judge Cardoso, and they have different opinions, and we would like to somehow aggregate their various opinions to the decision of the court. So what's more natural than just taking a majority vote? So here's what I did. You can look at the table, but you can see that there's something odd about the majority vote. So according to our rule, we have to say that the defendant is guilty if they had both the means and the motive. So a majority of judges thought they had the means, a majority thought they had the motive, but somehow a majority did not agree that the accused should be guilty. Okay, so this is our motivating question. So put it in another way, this shows that the majority function is not admissible for AND. Okay, and let me now spell out what this means. So a judgment aggregation function is a function f from 0, 1 to the n to 0, 1, which aggregates the opinion of all judges on some kind of matter. We say that such a function f is admissible for AND if the following holds. F of x and y is equal to f of x and f of y. Okay, so what's going on here? So let us go back for a moment. So x is the means column, motive is the y column, and guilty is x and y. When we apply f, then we get the bottom row. And what we want is that the bottom row satisfies this f of x and y. So this is going to be the third column. It's equal to the aggregated first column and the aggregated second column. Okay, which doesn't happen in this particular example. Okay, so now we can ask which functions are admissible. So let me pause for a moment to let you see if you can think of such functions. Okay, so here are some examples. So first of all, dictators. Okay, so if Judge Holmes, he decides what's going to happen, then definitely the accused will be convicted if they had both the means and the motive. Okay, this is maybe not such a good function. Other functions are the constant functions, which are even worse. But there's one more function, which what's known in the literature as oligarchies. Okay, this is an AND. For example, if we say that the defendant has the motive only if all judges agree that they had the motive, and the same for the means and for are they guilty or not, then this is also admissible. Okay, so these are all the admissible functions, and kind of we don't like any of them. Okay, so this is a theorem which is not too hard to prove, that ANDs and constants are the only functions which are admissible for AND. And what's natural to ask at this point is, can we find other solutions, maybe better solutions, by slightly relaxing the admissibility constraint? Okay, so we no longer ask that f of x and y is always equal to f of x and f of y, but we just ask it to hold with high probability over random x and y. Okay, you can ask whether random x and y is the correct distribution, but let's not worry about this for now, or at all. Okay, so this question was asked and answered by Ilan Nechama a few years ago, and he showed that if f is approximately admissible, so if f satisfies what's in the blue rectangle, then it is approximately an AND. Okay, and what does it mean quantitatively? So if the probability that f of x and y is equal to f of x and f of y, if this probability is at least 1 minus epsilon, then f is order n epsilon close to an AND. Okay, so why aren't we done? Because we don't like this dependence on n. We know other cases, and I'm going to present a few, where there is no dependence on n. So this is our goal, and this is what we will succeed to do. But in return, our dependence on epsilon is much worse. Okay, so before saying anything more about what we do, let me give some other examples of questions or results of the same sort. Okay, so one of them is EROS Theorem. Okay, so in EROS Theorem, there are voters and they have to choose among 3 candidates, but this is a ranked vote. Okay, so they have to rank the 3 candidates, maybe more similar to the way a program committee works. Okay, and we have a rule that we have to aggregate their opinions by looking at pairwise comparisons. Okay, so when aggregating their opinions about A, B, and C, we first see which of the voters prefer A to B, which of them prefer B to C, and which of them prefer C to A, and we aggregate all of these pieces of data separately. Okay, and once we do it, you can see in this example something bad happened. If we use majority for the aggregation, we could get something which is not consistent with any ordering. Okay, so EROS theorem says that the only way to avoid it is by letting one of the voters decide. Okay, again, a dictatorship. Gilkala proved that even if you just want this scheme to work on average, so with probability 99%, still you cannot really get far away from dictatorships. Okay, and this result does not depend on n. Here is another example, so linearity testing. You can read the story here. I don't think it's very convincing, but the point is that we replace AND with XOR. Okay, this is something that you all probably know. I'm going to explain it in a bit more detail later. But once again, we know that majority doesn't work, so you have here a counterexample. And this time, the only functions that work are XORs. Okay, so we've seen 3 examples, and now let me give 2 different interpretations of this kind of question. So the first kind of interpretation is from universal algebra. Okay, so in universal algebra, what we call the function admissible for AND is known as an AND polymorphism. Okay? In the case of EROS theorem, so let me go back a bit. So the constraint we have on each row is that of the 3 yes-no pieces of data, they cannot all be equal. Okay? Because that would create a cycle which does not respond to any order. Okay? So this is the NAE predicate mentioned here. And the only function admissible for NAE, the only functions are dictatorships. In linearity testing, we're interested in XOR polymorphisms, and we know that the only polymorphisms of XOR are XORs. Okay, so there are 3 examples here. So the only N polymorphisms are ANDs and maybe constants. The only polymorphisms of NAE are dictators, and the only polymorphisms of XOR are XORs. Okay, but these are all exact polymorphisms. And what we're interested in is approximate polymorphisms. Okay, now let me spend a bit more about this universal algebra interpretation by introducing the concept of truth functionality, which we'll see later in the open questions. Okay, so we've seen 3 examples, only 2 of them are truth functional. What does that mean? So a set of allowed rows is called truth functional if the last column is a function of the other ones. Okay, so for example, in our AND example, the last column is the end of the first 2 columns. And the same thing for linearity testing. But for NAE, it's not so. So for example, if the first column is yes and the second one is no, then the third one is arbitrary. Okay, so why focus on the truth functional setting? This is because of a result of Dokov and Holtzman. So they showed basically that the only interesting cases are AND and XOR. In any other case, there are no polymorphisms besides dictators and, in some cases where it's appropriate, constants. Okay, so the 2 most challenging questions are XOR, which corresponds to linearity testing, and AND, which is what we handle in this work. Okay, so much about universal algebra. And now let's move on to property testing. Okay, so let's go back to linearity testing. So we want to test if a given function f is an XOR. Okay, so we all know that XORs satisfy this identity that f of x XOR y is equal to f of x XOR f of y. And we can use this to test whether f is an XOR. We just choose x and y at random, and check if this equation holds. So if f is an XOR, then the test always succeeds. This is known as completeness. Conversely, if the test succeeds with high probability, or rather with probability close to 1, let's say 99%, then, so it turns out, f is close to an XOR. And this is known as soundness. Now, oligarchy testing is the same thing, but with XOR replaced with AND. Okay, and again, the natural test is to pick x and y at random and check whether f of x and y is equal to f of x and f of y. Now, you can check that completeness does hold, and what we want to prove is soundness. Now, Ilan Nechama proved soundness, but in his case, the soundness depended on n, and we want a result which does not depend on n. Now, before moving on, let me mention that very recently, this was subsequent to our work, Goldreich and Ron, they came up with an optimal or almost optimal test for this thing, but the test looks different. Okay, so now let's see if we can adapt known techniques for linearity testing to hold in our case. So first, let us recall these known techniques. Okay, so there are two ways to analyze linearity testing, at least. There are actually a few more, but these are the two important ways. One way is using self-correction. So this is from the original paper of Bloom, Luby, and Rubinfeld. Okay, so what's the idea? Instead of saying that f of x XOR y is equal to f of x XOR f of y, we put it differently. We say that f of x is equal to f of y XOR f of x XOR y for most x and y. Okay, and then we just take majority vote. So to know what the value of f of x is, we take majority vote over the right-hand side. And the surprising thing is that this thing works. Okay, so this is one method. The other method is Fourier analysis, and this is in a paper of Bellari, Coppersmith, Hostad, Kiwi, and Sudan. Okay, so the idea is to express the success probability of the test in terms of the Fourier coefficients of f. You do this, and you see that one of these Fourier coefficients has to be very close to 1. Okay, so this is another perhaps simpler method, which also gives better results in some sense, as we'll see in the open questions. Okay, so now let's see if these methods can help us in our case. Okay, so again, we have a function from 0, 1 to 0 to 0, 1, and we know that for most x and y, with probability 99%, it holds that f of x times y is equal to f of x times f of y. And we want to deduce that f is close to an end. Okay, so one method you can try to do is the self-correction. And recall that for XOR, we expressed f of x in terms of f of y and f of xy. But unfortunately, whereas XOR is a group operation, n is not, so we cannot do it. Somehow information is lost. Okay, so this doesn't work. The other thing you can try is Fourier analysis. So you can write down the formula for the success probability of the test, but you won't really get very far. You will just get some formula which is not very helpful. So somehow for linearity testing, we were lucky that the XORs, which were what we were looking for, were the Fourier characters, or something known as monomials. Okay, so maybe you ask yourself, what did Ilan Nechama do? So he used something like the classical analysis of monotonicity testing. Okay, he has some inductive argument which somehow corrects the function to an end. And that's why he gets a dependence on n, because he has to do it in n different steps. Okay, so all of these approaches, they don't help us. Now let's see what does work. And I'm only going to explain it very briefly. Okay, so this is our approach. So suppose that f of xy is equal to f of x times f of y with some probability close to 1. Our idea is to somehow reduce it to a strange eigenvalue problem, or rather eigenvector problem. So let us fix some x and take expectation over y. Okay, so what we get on the left-hand side is some sort of averaging of f at the point x. So this is what we denote here by t down f. So what is t down f at the point x? It's the average of f of z over all values z which are below x. Okay, this is also known as the one-sided noise operator. Now on the right-hand side, what we get is just lambda times f of x, where lambda is the expectation of f. Okay, and now if we do it for all x, then what we get is that, roughly speaking, t down of f is closed in some appropriate norm to lambda of f. Okay, so all that remains to be done is to determine the approximate eigenvectors of this operator t down. Now this is not particularly easy. There are several obstacles in doing this. Let me just say one thing about how we do it. So we use the fact that t down has a low pass effect on the Fourier expansion. Okay, so if you start with an arbitrary function and you apply t down, you're going to get a function with small tails, whatever that means. Okay, and then we apply Bourgain's junta theorem, a deep result in Boolean function analysis, to deduce that f is a junta. Now it turns out that because f is a junta, then we can somehow reduce the problem to constant dimension, and from there, it suffices to determine the exact eigenvectors of t down. Okay, so I'm cheating here a bit. Really, we want to understand generalized eigenvectors, whatever that means. But this is something which is feasible, and that's what we do. And this is these are the basics of our approach. Okay, I don't want to say anything more. If you're interested, you can take a look at the paper. Okay, so let me close with a few open problems, which our work raises. Okay, so the first one, so if you recall in Ilan Nechama's work, then if the test exceeds the probability 1 minus epsilon, then the function is order n epsilon close to an n. So we get rid of this n, but in return the dependence on epsilon is not so good. Now we have several different proofs, and each of them gives a different dependence on epsilon, but none of these dependencies are polynomial. But we think that the correct result should have polynomial dependence on epsilon. Okay, so this is one thing. A second open problem is to generalize our entire work to the general truth functional setting. Okay, so if you recall, we've seen three examples. We had N testing, we had EROS theorem, and we had linearity testing. Okay, only two of them were truth functional, N testing and linearity testing. And that means that in our table, the last column is a function of the previous columns. Okay, in the case of N testing, it's the N function. In the case of XOR testing, it's the XOR function. Now, if you recall, apart from AND and XOR, then in all other cases, essentially, then the only non-trivial polymorphisms are dictators and sometimes constants. Okay, so we would like to generalize all of this to approximate polymorphisms. Okay, we think this is an approachable problem. Yeah, I think this is something very natural to do. So I just want to mention again that this is known for EROS theorem, which is not truth functional, where the proof uses Fourier analysis. This is due to Gil-Kalai. Okay, and finally, one last open problem, which we think is interesting, is a list decoding version. Okay, so maybe let's start with linearity testing. So far, what we've said is that if this linearity test passes with probability close to 1, then f must be close to an XOR. But actually more is true. If this test passes with probability better than random, so better than half, then f cannot be arbitrary. This says something about f, and what this thing is that f correlates with some XOR. Okay, and the only known proof of this is via Fourier analysis. So this local decoding proof doesn't generalize to this statement. We can ask exactly the same thing about n. What if we have a function f that is obviously not arbitrary because it passes this test with probability better than random? Can we say something about it? Maybe it correlates with some n, maybe something else. We don't know, we're not sure. Okay, so these are the three open problems that we think are most interesting that our paper suggests. So thank you all for listening. If you want to know more, you can read our paper, or there are also some lecture notes on my homepage with more details on how our actual proof goes. Okay, so thank you for listening.